Hello everyone. We were looking at different soil water characteristic models and hydraulic conductivity functions for the estimation of flow through unsaturated soils. So, we are preparing ourselves to take up the task of understanding the flow through unsaturated soils. Before we can get into the flow, we need to understand the SWCC models that are available for obtaining smooth soil water characteristic curves and hydraulic conductivity function, well established HCFs from the measured water retention data from the laboratory or from the field, and either by measuring the hydraulic conductivity function data as well or prediction from the SWCC model. So, this whole process is done in this particular manner. In the first stage, we were obtaining the soil water retention data as of which is a relationship between volumetric water content versus matrix suction. Often this data also we may not get directly because we may need to use different suction controlling or suction measurement techniques in the laboratory for the estimation of theta versus psi over a whole range of suctions. So, often we get in terms of maybe gravimetric water content W. So, then using the relationship between W and theta by using the density of soil, how it varies with either drying or wetting, knowing this data we can convert to theta. Once we convert to theta, we can plot theta versus psi. So, we get a discrete data like this. The theta equals to theta s corresponds to very small suction or suction is close to 0. So, that is a saturated volumetric water content which is porosity of the soil, and as the suction increases the theta value decreases. So, this is the discrete data we obtain. However, this discrete data may not be directly useful and we require a smooth well defined function between theta and psi. We utilize several existing retention models such as Van Ginsten model, Van Ginsten model of 1980 or Fredland and Sching 1994 model, or any other model. You can use Brooks Corey also, BC model, which is maybe 1964. But however, with the BC model we have a major issue that up to the air entry value we have a theta equals to theta s, and beyond that it decreases non-linearly. However, here the function is not smooth at air entry value, therefore we may not get a smooth function as we get with other models. So, when we use these models, these are the retention models, we can obtain a smooth function like this using some optimization techniques that will be discussed now after this slide. So, using some optimization techniques we can obtain a smooth function like this. So, then once we obtain a smooth function using different statistical models such as Molam model or Budin, such as statistical models one can use, or even Fredland Sching uses Kunz model. So, such models could be used to obtain hydraulic conductivity function. In the last class, in the previous class, we discussed how to obtain the hydraulic conductivity functions by knowing the SWCC model parameters. Once A, M and N parameters in Van Ginsten are A, M, N, CR parameters in Fredland Sching model. Once these parameters are known, using different statistical models like Molam, Budin, etc. or Kunz. So, we have analytical solutions for few cases, and for few cases we have to solve numerically, and we can obtain hydraulic conductivity function like this. So, once we have SWCC model in the second stage and hydraulic conductivity function in the third stage, using these two functional forms we can use to model the flow through unsaturated soils. Either it could be infiltration problem through soils. As it infiltrates, the hydraulic conductivity starts increasing. So if we have wetting data, then we can directly utilize, and similarly the suction value decreases because there is a suction gradient that exists within the soil mass, because of which there is a flow that is taking place. So therefore we can utilize this equation as well. Provided these are wetting data, then we can directly utilize to understand how the flow takes place through a initially dry soil. Similarly, if you have a drying data, drying SWCC and drying hydraulic conductivity function, then we can understand the evaporation behavior or drainage behavior through initially saturated soil. As I discussed in the previous classes, that the one-dimensional flow through partly saturated soils can be understood using this kind of equation, which is similar to the consolidation equation. So here you have the dependent variables theta, which is again a function of suction. So dou theta by dou t is equals to dou by dou z of k hydraulic conductivity, which is function of suction. Therefore this is hydraulic conductivity function times dou psi by dou z plus 1. So we will see why we get plus 1. If you have a horizontal flow that is taking place, then you will not have this plus 1. So if you have a vertical, then plus 1 is added. That we will see in when we discuss about the flows. So if you simplify this or to modify this equation to get the same dependent variables on either side of the equation, then you can convert to suction throughout, then you will have a slope dou theta by dou psi times dou psi by dou t. So this is the slope of the soil water characteristic curve, which is called the specific moisture capacity, which is equals to dou by dou z of hydraulic conductive function, and this is the same as the earlier form. Now the k of psi m is a hydraulic conductivity function and psi of theta is the soil water characteristic curve. Here we require smooth functions to solve this equation. Another important point here is the slope of the soil water characteristic curve should be defined at every point. That means the slope or derivative of the soil water characteristic curve should be well defined. In case of Brooks-Corey method, the dou theta by dou psi is not valid at air entry value, because at that inflection point, which is a very sharp inflection point at air entry value, so therefore this value is not valid. So therefore that is the reason why we require very smooth functions like hydraulic conductivity function and SWCCs to solve this particular equation to get theta, volumetric water content, as a space and time. So this is the data we are looking for. So when we give this as an input, we get this theta. How to get soil water characteristic curve from the measured retention data? We have several optimization strategies like gradient based optimization. Those are classical methods to minimize the error between experimental data and theoretical data. So here I briefly discuss how this is generally done. From stage 1, that is a measured data, measured water retention data, to smooth soil water characteristic curve, how we obtain. So generally we build error functions are called objective functions. We build objective function, say which is a function of say x. X is the variable which we want to determine, or the model parameter we want to determine. So how this function, what is this function? Objective function. Objective function can be built using the measured data. So for example, this can be determined as this. So the measured data, difference between measured data and the theoretical data. So say you have n number of points, n number of measured data points. So then volumetric water content theoretically determined for different suction values minus theta m, that is measured I. You can obtain square divided by number of data points you have. So this is root mean square error they call. So essentially when you have SWCC data, like this, theta on y axis and psi on x axis. For different values of psi, you have say n number of data points. For corresponding n number of data points, you can assume one particular VG model. So, which is maybe theta equals to theta r plus theta s minus theta r times 1 by 1 plus alpha h power n whole power m. Here we assume one set of alpha, m and n. Here you can write in terms of a also, you can write a psi or psi by a. This can be written in the form of theta r plus theta s minus theta r times 1 over 1 plus psi by a power n whole power m. So, this is the general form which is used in geotechnical engineering. So, here when you use psi, the a has units of kilopascal because psi has units of kilopascal. Here alpha has units of 1 over meter because h is substituted in meters. So, therefore, either alpha mn or simply a, m and n. So, you can assume one set of these model parameters. You can give a value to, this is related to air entry value. If it is sandy soil, you can give say 2 kilopascal, he has an initial value. If it is a clay soil, you can give a very high value, say 1000 kilopascal or something, and you can give some values to m and n, maybe n is equals to 1.5 or something, and m value you can give 2 or any value. If m and n are related or constrained, then you give the values accordingly. So, this is called initial guess. So, this is the initial guess that is given. So, when you give this initial guess or you substitute these values, then you can obtain theta theoretical values. So, that may be somewhat like this. So, this may be theoretical and this may be experimental. This is experimental or measured, this is theoretical. So, then for any given suction value, so there is an error between measured and theoretical. So, this is what we are trying to minimize. You build an objective function, that objective function or error function contains what is the error between this data point and theoretical data point, this data point and theoretical data point. You can use sum of squares or root mean square or mean square or any norm could be used to define a error function. Once error function is defined with respect to any given model parameter, say here the error function or the model parameter here is x, x could be a, m or n. If you have only one model parameter to determine, you may have an objective function like this. So, our objective is to minimize the objective function, objective value or error function value, and what is the corresponding x, that is what we are trying to determine. So, this can be solved using simple optimization. So, you can determine an initial guess, maybe this is the initial guess xi and this is optimum. Our objective is to get x optimum by assuming some xi, xi could be here or anywhere on this curve. So, we use different gradient techniques, and using gradient techniques, a simple gradient technique is the objective function with respect to x should be 0 at optimum value. At optimum value of x, when x equal to x optimum, this value should be 0, this objective function should be 0. So, in case of the present thing which I was discussing, for example, if you have a dependent case where the objective function with respect to say a and another axis you have m, and for example, if you have m and n restraint condition, m and n are related. So, in that particular case you have some functional form, a 3-dimensional form. So, where you have one particular model parameter where one particular set of model parameters A and M where the objective function is lowest or minimum. So therefore dO by dm and dO by dn should approach to 0 at optimum value. So that set of m and n we determine. So we build an objective function here O in terms of A, M and n if you have 3 parameters to determine, or simply A and M only 2 parameters to determine, then the objective function is minimized. So this is minimized. There are several such optimization strategies using gradient, where sometimes they utilize double derivative also, and they solve. These are called classical optimization algorithms or strategies. They utilize the gradient of the objective function with respect to the model parameters, and they determine the optimum parameters. So such strategy is used and a software is built which is called RETC, RETC, to estimate soil water characteristic curve, a smooth SWCC function from the measured data, where we can utilize Van Jenisten model or Brooks-Corey model, and in Van Jenisten again you can utilize different restraint conditions, A, how M and N are related, or M and N are independent, and several such cases could be utilized, and we can obtain a smooth function. And now I will demonstrate. This is a free software, freebie, which is developed by Van Jenisten and Lees, Yates, etc. And in 1991 there are several improved versions are available. One can simply download. There is a website called PC Progress. If you give the keywords as PC Progress RETC in Google, you will be guided to the web page and you can download the RETC software, which is a very simple software. I will demonstrate it now. So this is the RETC software. So initially when you select a file, a new project, here you can give some name, and you can give some description, say demo. Here it will ask you what are different problems, type of problem, scale units, type of retention or conductivity model, soil hydraulic parameters. So when you choose the type of problem, a new window opens up. Here it says welcome to RETC, and type of fitting you want to do, both retention data and conductivity or diffusion data. So retention data is soil water characteristic curve data, and conductivity or diffusive data. Generally we do not have conductivity data. I have some retention data for loam soil from Arya Paris paper 1981. So I will use that data to demonstrate how it fits using a gradient based optimization algorithm called Levenberg-Marquardt algorithm. So I will select only retention data because I have only retention data, and when I select next, I can choose different units. Here the input for the suction should be done in soil water potential, that is suction head should be substituted. Therefore we select meters. I can substitute suction head in meters or centimeter or mm. So generally we have suction values, very high suction values such as 500 kilopascal, 1000 kilopascal, etc. generally in for fine grained soils, which we deal in soil mechanics. So therefore it is better to select in meters, and it could be anything because we are not dealing with time units now, because we are not estimating hydraulic conductivity now. So here for the inverse problem, if you have, then maximum number of iterations, number of printed iterations you can choose. I will leave everything default. So here you have several models, Van Jenisten variable M and N model. So this I have discussed, where you do not have any restriction between M and N, only the restriction is that N is chosen to be more than 1. N less than or equal to 1 results into non-physical data at suction value close to 0. So you have corresponding conductivity models also you can choose. You can choose Mulam or Burdin. So therefore, accordingly, once m and n parameters are estimated by optimization, the hydraulic conductivity functions are also determined immediately. So you have Van Jenichen model, m equals to 1 minus 1 by n. This is a particular solution. So I have discussed this. When we made k equals to 0, you have a particular solution. For that, there is an analytical solution available. So corresponding analytical solution, you can choose again Moulomb model. Similarly, in combination with Burden, they derived another solution k equals to 0, for which the hydraulic conductivity function has a particular solution. So for which m equals to 1 minus 2 by n. Similarly, you can choose Brooks-Corey model or Brooks-Corey along with Moulomb and Burden, or log normal distribution or dual porosity models. These models I did not discuss, but other models I have discussed in the previous classes. So you can choose any model. We can choose say Van Jenichen m equals to 1 minus 1 by n model, and correspondingly the Moulomb can be selected for hydraulic conductivity function estimation. So then if you click next, it will ask you, it will show you different parameters that are available, that is theta r, this is theta r, the residual water content. Do we know this data or no? If we do not have, we can fit it. Theta s, if the data is known, then you do not need to fit it. You do not need to fit it, you can select this data. So as of now, I will leave it as it is, and alpha value I will fit, n value I fit, and ks if I do not have, if I do not need to fit, then I can select some value. Here I am leaving a default value like this. So now you can choose from this menu different soils, possible soils you are fitting for. So actually I am fitting for loam. This information is also not required for the optimization, but here this information is used so that the initial guess will be generated based on this data. You can recollect what I said. For the gradient based optimization techniques, we require an initial guess. Based on the initial guess, using the gradient, we move to the next step and reach the optimum value. So how to choose the initial guess is a big issue. See here the initial guess is chosen based on the type of soil. So if you select loam, I have the loam data, so I select the loam. So then initial guess will be taken accordingly. Then if I select next, so here I can input the pressure versus theta. Here pressure should be inputted in meters. So I can input the data, that is 13.94 meters pressure corresponding to a theta value of 0.099 and pressure value of 4.255, and corresponding theta. As pressure is decreasing, the theta value should increase. So this is 0.12, pressure is 1.608, so the theta data is 0.172, and this is 0.539, this value is 0.248, and this is 0.0953, and this data is 0.364, and this is 0.0539, and this value is 0.39, and this is 0.0181, and this value is 0.42, and 0.06, this value is 0.434. So this is the data we have. So here you can give weightage based on whether the measured data is accurate or not. There may be slight chances of when you do the tests several times. So this is a measured data, therefore there may be some small error that could be there. So you can give weightage whether this data is reliable or this particular data point is reliable or not. So here I am not giving any weight or anything, I am just leaving the default values. So then when I go for next step, do you want to save the input data before executing a REDC? I select OK. then it asks you, do you want to run the application? Yes. So then it will show you this one and you need to give enter. So once you enter, so you have the output file. This is the fitting that has been done. So here the water content is drawn on y-axis and pressure head, so that is in meters, is plotted on x-axis. So these are the data points. So these red marks are the data points that we have inputted, and this line is a fitted line, and this is hydraulic conductivity versus pressure head. So which we cannot see it here in log scale. If you see log conductivity versus pressure head, this is how the hydraulic conductivity varies with suction head. As the pressure head increases, the hydraulic conductivity decreases. So this is the output file, and if you see the graph, this is the water content versus pressure head, which is very well fitted. So this red marks are the data points inputted, and this is this black line is the fitted curve. So when you plot the conductivity in meter per days in log scale and pressure head in meters, if you plot, as the pressure head increases, the conductivity decreases. So this is the plot you have, and we can see the Red Sea output file, which contains the information of what we used. We used a Moulomb based restriction, that is m equals to 1 minus 1 by n used, and this is the initial values of the coefficients. Theta r we gave 0.078 and theta s 0.43. So this initial value is not fitted, but this is selected as an initial guess, but 0.43 this value we have inputted, and alpha, n, m are taken as initial guess, and Ks we have given as 0.2496. So then after the analysis, the R square you got is 0.987, a very good R square value. So the nonlinear least square analysis is done, and finally this is the output. The theta r is estimated to be 0.0535, and alpha is 7 and n is 1.48. As is the n and m restricted case, so once we get the n, we can determine the m as well. So this is the data we get. So once we get the m and m are n and alpha values and theta r, so these three parameters, unknown parameters, are known, and we have the other known parameters like theta s and other data we can use and plot it in Excel on our own, and that is how the SWCC smooth function is obtained by Red Sea software. So this is how Red Sea, a free software, could be used for the estimation of smooth soil water characteristic curve. So we can also obtain the hydraulic conductivity function. However, if you are interested in using Fredland and Sching models, the Red Sea software does not allow you to use Fredland Sching. So then you need to use any other software like GeoStudio, but these are commercial softwares where you can generate, or you can write simple code in MATLAB and you can optimize. So the gradient based algorithms have some issues, such as the initial guess needs to be thoroughly examined, because generally the objective functions may not be as smooth as I have shown. So the objective function could be like this, but because this is objective function versus say x, but because we are using some experimental data, measured data, there may be some error. So this may not be as smooth as this. You may have some roughness and you may have a data like this. So in that particular case, so this may be your global minimum, but your function may get stuck here itself at local minima itself. So if you choose an initial guess somewhere here, this may be your initial guess, and it will traverse and it will get stuck here itself. It may not reach here, or it may be 0 here itself. So the objective function gets 0 at local minimum value. So therefore the estimated parameters may be erroneous. So therefore there are some global optimization algorithms. So those are based on nature inspiration. So such algorithms are genetic algorithm, anti-colony optimization, particle swarm optimization, In that there are many variations. Of course, in genetic algorithm also there are many variations, and anti-colony also there may be few variations. In particles form optimization there are many variations like quantum behaved PSO, perturbed PSO, which is our work from our research lab, and B colony algorithms, etc. So these algorithms, very limited algorithms have listed here, but there may be enormous number of algorithms based on the observations in the nature. So here for example, if I describe ant colony, the way the ants move from their colony to the food sources by optimizing the path between the colony and the food source, that is one of the inspiration for building an optimization algorithm. There is an optimization involved in doing that in the social behavior of ants. So based on that the algorithms were built. Similarly, the particles form optimization is based on the behavior that is exhibited by the flocking birds and fish colonies, etc. So birds, they try to fly in a V formed shape, and there will be a leader and there are followers, and they usually form this V shape and they fly to minimize the drag force. So there are several rules to maintain such V shape and then while flying. So such optimization behavior is brought into the algorithm, and which is used for solving several engineering problems. So for example, the particle swarm optimization, which has simple rules. For example, you have two parameters x1 and x2. You can choose initially some number of solutions on the set space. This is the set space. The x1 in our case could be A, and x2 in our case could be M or N. So two parameter optimization problem, we have this is the set space, this is the set space. We know the limits of this set space as well, because A can vary only between some particular range, say 0 1 kilopascal to minimum 1 kilopascal to a very large value like 5000 kilopascal or 10,000 kilopascal, because this is related to air intervalue. And M also, M or N can be restricted in a given range. Now possible number of solutions are chosen on the set space, and each solution indicate a set of A1 and M1, and you choose another one, this has A2 and M2. These are the two possible solutions for our problem, and similarly you have chosen n number of such solutions on the set space, I equals to 1 and this is I equals to 2, and similarly you have n number of solutions. Now I equals to 1, corresponding to this you can obtain the objective function O1, and corresponding to I2 you can obtain the objective function O2. So now once you have the objective function O2 and O1 and O2, you can compare these two, and if objective function is lower, this value is lower than O2, that means the global minima could be close to this particular value, close to. So what you could do is you can make this particle to move in this direction, in the direction of 1. So one possible way of doing that is, for example, you have one particular particle here which is at distance say 0 and 2, and another particle are we call particles. These number of solutions are called particles. It could be birds also. So that means here another particle which is located at say 4 and say 5. How to move this particle to this value? So directly to move this particle to here, what you could do is the difference could be added to this value and then it will jump into there. So for example, the difference is 4 and the difference is 3. If you add this point to this and this point to this, it can directly jump here, but we do not want to do that. Directly it should not jump, because this may not be the global solution. It should only move in this direction. So for that what you could do, you can multiply with some factor, so see theta or alpha or something, So, this is less than 1. So, then it can jump to a new solution in that particular direction. So, similarly, you compute the objective functions of all different particles, and whichever has the lowest objective function, all different particles will move towards that particle. For example, this particle has the lowest out of all the different particles, then all different particles will start moving towards him. So, one iteration is complete. In the next iteration, they have new positions. So, again you can compare all the objective functions and you can obtain the what is the global best, and also because they have their own experience to move from here to here, they can compare within their history who is best, this position is best or this position is best. Based on the local best and the global best, the particle will start moving towards the optimal solution, and finally at the end of the iteration, once the search is complete, all the particles will converge to one particular point, that is the local minimum. So, I will demonstrate this. So, this is one particular problem for diffusion problem, where I have two parameters to optimize, that is diffusivity, diffusion coefficient and retardation factor. This is a contaminant flow through saturated soils for that particular problem. So, initially I have chosen number of particles on the search space, say these are the number of particles, and they started searching and moving towards the global. So, this is initially the best solution. So, everybody started following this fellow and then they started coming close to, and this also started searching and found that there is a better solution in and around. So, it also started perturbing, and finally all the particles at the end of the search process, they converge to the global solution. So, that is how we search the global solutions using swarm intelligence or nature inspired algorithms. So, there are many such algorithms, so one can use to determine. So, once you get the smooth soil water characteristic curve using optimization techniques, we can determine the hydraulic conductivity function, that is stage 2 is SWCC, obtaining smooth SWCC, stage 3 is obtaining K function. So, once SWCC is obtained, the K function can be determined using either analytical solutions if they are available or numerical solutions. If Van Jenichen model with some restrictions are chosen, m equals to 1 minus 1 by n or something, then you are using Molam model, then corresponding hydraulic conductivity function is known, the solution is known as we discussed earlier, and you can obtain. Similarly, Van Jenichen model using burden equation is known, then we can utilize the particular solution which was derived and we can get the hydraulic conductivity function. Similarly, if you are using Mn variable case, so then corresponding Kr in terms of incomplete beta function could be used to obtain the hydraulic conductivity function. Similarly, several number of hydraulic conductivity functions can be determined based on what type of SWCC model is utilized. This is how we obtain hydraulic conductivity function. So, once we have SWCC and hydraulic conductivity function, once we have these two functions, well defined functions, we can utilize them for the flow problems. So, once we enter into the flow, we can understand how these functions can be utilized and solved. Thank you.